Okay, let us go ahead and resume. We will continue the story of working with mechanical systems and like how we start using the building modeling tools to wrap them all together. We're just kind of like just do a reality check in terms of like how this is seeming so far, and is it sort of making sense, or is it kind of connecting? Like, yeah, okay, excellent. No worries. It's really, again, what I think the biggest challenge for people tends to be is it's more the physics of the situation, the science behind the situation, than it is the modeling. If you can actually try to like work with relatively realistic constraints, get all or within the bounds of what is physically possible, it tends to work out to be pretty, I won't say easy exactly, but the modeling tools generally cooperate and make nice systems for you. Let me go ahead. I'm going to do a couple more things to this plumbing system just to kind of complete the story. We're doing pretty good on this restroom on the one side, although it still kind of bothers me over there that I don't have that connected just there. I'm going to put a riser in here and then connect it. It'll probably make more sense. Often I'll start with the notion of putting a riser in, putting some sort of a vertical connection in between the different floors. It'll actually typically be one of the first things that I do. And the reason I like to do that is, well, it's almost like, I'm moving back from the source or the end point to like all the different fixture units, or all the fixtures that are sort of generating the loads. And it's nice to kind of like, what would I say? Think about kind of doing that in a very systematic way. So even over here, you can sort of see here's all these different little like fixtures. Oh, these are what it looks like the single line. Yeah, it's interesting. There we go. A little more detail in terms of what's going on. We can start to see how these things are connected together. But let's think about actually putting some sort of riser in here. Okay. Drawing pipes vertically is always one of these challenges I have. Drawing vertically, because pipes tend to like, it's easy for me to draw things horizontally. Drawing them vertically, can do it, but I think we just need to like go through and give it a little bit of help in terms of making it happen. What I will tend to do, only because it sort of makes it easier for me, is whenever I want to draw something vertically in a specific location, I'll tend to put a reference plane in that then allows me to draw on that surface. So for example, if I want to write in here, actually I'll even back it off a little over here. Put in a plane, I'll call it my risers. The reason for putting that together is now if I draw in an elevation view, I can draw right on that plane and have some control over where things show up in the distance. If you don't put that in there, you can still draw. It's just you'll have a little bit hard time controlling where things will show up in the background. You may have to sort of move them like in 3D space to make it happen. But if I want to go through and put some sort of riser in there, for example, a pipe, which is a sanitary pipe, okay, which is 4 inches. Let's see if I can sort of adjust this. This is always this thing where it sort of messes me up a little bit in terms of just exactly how to do this, because I think I ought to be able to draw this. I'm wondering if it's just not going to let me draw it in 3D, or if in 3D, if I have to say, set the work plane over here to my plane risers. Maybe that'll let me do it. I always have to think about the precise workflow about this. So I'm in 3D, I set the work plane. Let's see if I can try this again. Pipe, 4-inch pipe. No slow. Well, let me draw on this view. This is interesting. Let me go ahead and try drawing it in an elevation view instead. But again, I always fumble around on this a little bit, but we'll see if we can make it work. I'm going to say the east side mechanical view, or let me go to the east side plumbing view. Okay, actually, let me warn you about that. Notice in these plumbing views, these things that are designated as plumbing views, I'm seeing plumbing. If I go to these mechanical views and I go to east side, I don't see the plumbing lines and things like that. I see the fixtures, but I don't see the plumbing lines. Let's talk about that for just a second. Every view, in addition to having, lots of other properties like the scale and the coarseness and stuff like that, actually has some notion of a discipline associated with it. So There's an overall discipline, which is plumbing. Subdiscipline here is also plumbing. Let me go and distinguish that from over in the HVAC views. If we go here, yeah, here we have, oh, what's my big discipline here? It's mechanical, and my subdiscipline is HVAC. What happens is, as we start layering in more and more information into the project, we can filter our views in different ways to highlight different types of information that are good for different subdisciplines. So, you know, you have to start thinking about every project or every drawing having a discipline to it. You know, this elevations, or these elevations right now, which belong to plumbing, or these elevations, which are part of HVAC under mechanical, how that hierarchy is determined is really just all by these, you know, controls right over here. So since I am HVAC mechanical, if the subdiscipline is HVAC, the bigger discipline is mechanical. If I wanted to have this elevation move to a different discipline, I could make it under lighting mechanical, and it's just showing up under a slightly different part of the browser right now. It's really just a categorization scheme for what it is you're going to be showing in that view. But let me go ahead and put that back over HVAC. I'm going to go over to the plumbing related ones. And again, what's the difference in the plumbing related ones? It's really just that the things that are turned on are really related. You know, under mechanical, actually hang on you. Yeah, plumbing, subdiscipline plumbing. It's because it's plumbing right there. It's just really, it's going to show me things that are plumbing related. So if you're not seeing things and you know they're there in the 3D model, pay attention to which discipline what the discipline is of the drawing that you're looking at right now. Okay. With all that said, I'm still just trying to draw this riser. Let me see if I can get it in there. I'm going to draw on the plane. I'm going to choose pipe. Slope off, 4-inch. Sanitary system. I think I ought to be in good shape. I put it perfectly in line, that's okay. I don't actually have to put it perfectly in line with those. Yeah, if I do put it perfectly in line, it'll be a little bit easier in terms of fewer bends and jogs to actually make it join up. It actually hasn't joined in 3D just yet. You'll see in 3D, I'm still offset by a little. In fact, I'm way off there. Which makes me think about, well, let's go back to that again with the risers. Yeah, I'm honest confessionals. I always have trouble placing these things. -8 feet. Why is it -8 feet? I don't know. Try putting the other wires in. We'll see if we can sort of figure out a pattern to this. Okay, let's go through, and I'm going to put a little 1-inch. Make it a 2-inch domestic hot water. I'll line it up here. There's that offset. That's the thing that's making me wonder right there, because that's, I put it at 0. Let's try that. I think now it'll draw on the plane as opposed to being 13 feet off the plane. Let's see if we can try to test this. I'm always looking for a test to see how true things are. Let me go through, I'm going to put the other one in there too, and we'll see if my theory is right. Domestic cold water. 2-inch pipe, okay, again with an offset of 0 relative to the drawing plane.
Where did you choose to draw relative to the drawing plane?
Let's go back to 3D and we'll see if I make this make sense. Nope, they're all still out there. It makes no sense in terms of the offsets. I have no idea, because let me try this. Let me turn on where the drawing plane is. There's the drawing plane. That's just controlling the height. You know, at this point, I cannot tell you why there's a drawing where they are.
It's offset, I think, -8.
Yeah, well, it looks like that. I know I want it to be that. You know, that feels so attractive, right? You want it to be that. But then what if the offset was 0? It's offsetting vertically, but it's not doing the horizontal offset. I don't know. I'll see if I can figure that out. It's It's definitely sort of messing it up, but what I'm going to do is just going to grab them all and just move them in. This falls into that category. You know those things that you know you don't know? And yeah, this is one of those things. I know I don't know why this works, but we'll sort of, I guess I work around it. But we'll see if we can figure that out. Let me turn that off. So now I have 3 different risers in there, and what I should be able to do is I can take this pipe and say, oh, actually, for the pipe, I don't have to do it connect into. Let me kind of do it from the top, and you'll see. I'll even move them in closer. As the what? Oh, I don't right offhand. I could try doing a line and make it do that. Let me see if I can align the center of that pipe. It's like I'm like aligning half a pipe. See, I can't change the pipe. It's this very funny thing in terms of like trying to get it in there. But I think it's really more of like drawing center lines and trying to get it to line up that way. In this case, I just happen to be really lucky. I'll let me do something else and we'll see if we can kind of make it not so lucky. Okay, what I'm going to do is I'm going to pull the end of this pipe really right to that sanitary riser. Okay, and with any luck, it's going to go through and join itself. Let's see how it actually did in 3D. Okay. In this case, it didn't do something very smart. It actually kind of capped it off. Let me go through and take out that elbow because I don't want that to have happen. No, I really want this riser to go up to the 3rd floor as opposed to just stopping right there. What I can do is now just pull it in from the side, and then it'll kind of make the right kind of connection. And this is that sort of just fussing that you end up doing sometimes with all this. Let me pull this one back. What I often do is I end up pulling things back and then pulling forward and seeing if I can make it hit that. I think that is on the blue now. Okay, it's connected into the blue. That one's now connected into the hot. Okay, it's joining those things in. And now let me test this theory. My theory is that since I do have this, I should now be able to do a connect into from here to that. Yeah, and it joined in properly in terms of doing that. So what would I say? A good way to approach this is I would actually start by putting my risers down first as opposed to what I did here. Sort of figure out where the big vertical connections are between the floors. Then go through and figure out where the big laterals are, just where those big horizontal surfaces are that are at least feeding out towards the fixture locations, and then do the connection from the fixtures to the laterals. Just kind of connect them in that way. And I think that'll actually be the smoothest way to go through and do that. Okay, but by doing something like that, we've actually started to create these different systems that'll all work together. The nice thing is each of these different systems has a lot of information stored about it. It's not only that we've gone through and modeled them, just sort of understanding physically how they're going to come together. Let me go through and take a look at, under View. I'll bring up something called the System Browser. You'll see I have several different systems defined right now. I have 4 piping systems. So what I have going on, I have 1 sanitary system. Not sure why it thinks I have 2 different cold water systems. Looks like there's one over here, but there's nothing assigned to it right now, so maybe I'll delete that system. But within this, you start to see that, the fixtures are being taken care of. We sort of learn a little about in the system For example, on the cold water side, I can tell you that if I look at all the different fixtures, I have to be able to provide up to 39 gallons a minute flow to supply that system. Domestic hot water, I have to be able to provide up to 4 gallons per minute to supply that one unit there. On the sanitary side, it doesn't have a flow right there. But all these systems start tabulating from a performance standpoint too, that we can start thinking about what the loads are on those systems and ultimately, what we have to be providing downstream to supply all those different things. And we can even start optimizing it a little bit in terms of the sizing of everything so that the right kind of size is delivering the right material or the right whatever's necessary for all the things that are downstream. If I added another 12 toilets down the line here, you would find out that this feed pipe would have to get much bigger because theoretically more people could be drawing off of that. So plumbing systems, that's the general scheme for plumbing systems. Let me go ahead and kind of shift our thinking a little bit to the mechanical systems, the HVAC systems and how they work. Because it's kind of a very similar sort of idea. In many ways, I think they're even a little bit easier. But let's think about what you have to incorporate into your design when you're thinking about an HVAC system. Okay, for heating, ventilating, and air conditioning, let's think about what are the big criteria that ultimately drive the design. At some level, we have a certain amount of space, and within that space, we have loads on that space. So, the fact that we're in here as living, breathing, heat-generating organisms, we're creating a load on that space. Our computers are creating loads on that space. All this lighting is creating a load on that space. It's all generating heat that ultimately may need to be cooled away. There's loads that are coming from, just the fact that we're losing heat to the outside of a cool day like this. If we're trying to keep the space cool, heated, we're losing heat. We may need to be supplying heat back to the system to go through and kind of keep us to what's considered to be a comfortable level. And ultimately, as we design these things, there are ranges of comfort levels that we try to keep things at to kind of keep the buildings very serviceable. And we can have a very big impact on the design of all these systems just by choosing what the set point is of the system. Even in a room like this, how much variation can they be? Does it always have to be right at 76 degrees? Or can it get up to 78 or 80 and then kick on the air conditioning to bring it on down? And just really what the range of comfortable, allowable temperatures will be. And sort of the more flexibility you tend to give the system, the more energy efficient they are. If you're really, really precise about the fact that it always has to be a specific set temperature in this room, you might be heating and cooling just all the time, trying to keep it maintained to that because, when we're in here generating heat, you may need to cool the room. Later on, when no one's in here, you may need to be heating the room to go ahead and try and keep it that way. Yes, heating and ventilating tends to be kind of a very complicated sort of system to design overall. Another major consideration, though, that you don't think about as being one of the big drivers, but is this notion of just the ventilation side, just the freshness of the air in the room. And every room, depending on its use, has a certain requirement for really how much fresh air you have to be introducing all the time. And honestly, that's probably the bigger driving consideration of how these types of systems are designed. So let me kind of see if I can kind of bring up some general guidance about this. See if we can sort of make some sense out of this. Okay, these are recommendations for number of air changes per hour for different types of rooms. Okay, and the idea within this is the more air changes per hour that are required, the more air we're moving through it. Really, the more kind of mechanical ventilation we have to be providing through this. So let's see if we can figure out, like at a courthouse or something like that, 4 to 10 air changes an hour. Okay, no worries. Minimum in general is 4 air changes per hour. A bakery has actually 20. A bar has 20 to 30 air changes an hour. So why is that? Why do some spaces have so much more of a requirement in terms of changing the air all the time? Yeah.
Well, one would be like the number of people who are using that space and the density.
Mm-hmm. Yeah. it gets to, it's the people and the density and the use of the space, and a lot of it starts getting into the noxiousness of the fumes that need to be taken away. It's all these kind of different things. Like a paint shop has like 15 to 20 air changes an hour, whereas kind of in general around 4 air changes an hour. Auditorium's a little bit greater. Yeah. And these are guidelines about, in a big auditorium, if we don't move the air more than in a typical classroom, yeah, it just tends to start feeling, stale or a little locker room-like in terms of just getting a little bit overly humid. So let's think about how that actually plays out. So if we start with this notion of basically 4 air changes per hour, we got to translate that into something that we can go through and relate it to. So let's take a room like this. Okay, this room is, let's try to figure out how many cubic feet we think are in this room, because we're going to take that air changes per hour and change it into cubic feet per minute, which is the way we tend to think about these. So how tall is this room, would you guesstimate? Yeah, around 10. And how wide is that room going that way? And the little 2x2 ceiling tiles are a pretty good guesstimator. 1, 2, 3, 4, 5, 6. Okay, let's say it's 20. And how long is the room that way? I'm guessing 40. What do you think? Okay. So, mathematicians in the crowd, multiply that all together and come up with clearly, you're not bouncing my checkbook over here because. Okay, 8,000 cubic feet more or less in this room. 4 air changes an hour. That means I have to go through and move around 32,000 cubic feet per hour. Okay. Which then translates into how many cubic feet per minute? What's 32,000 divided by 60? Anyone at all?
532.
Oh, you're good. Okay, that would be minimum. Okay, if we were an auditorium or something like that, we want it to be, somewhere between 8 and 15. So this might be 1,000, might even be 2,000, depending on, but yeah, that's giving us a range, just so you sort of know where those things are coming from. Yes?
When you're sizing your equipment, can you take into account the natural use of the building? So if, like the auditorium, or maybe not as much for an auditorium, but for like a barber shop, if people are opening up the door to come in and out, does that factor into it?
It does factor into it. Ultimately, it does factor into the number of air changes. I think, though, when you're sizing, you sort of have to size for the worst case.
What about like passive heating and cooling?
Passive heating and cooling, okay, they will factor in from the heating and cooling side. What's interesting about this is just the amount of air that I'm going to move, quite independent of the fact that that air needed to be heated or cooled to kind of maintain a constant temperature. Like, basically, this much air is going to move through the space, and sometimes that air may have no heating or cooling, sometimes it may have heat introduced, sometimes it may have cool introduced. Okay, that's just an amount of air you have to move through a space. So the weird thing is even if you do have like a radiant floor system, or you're really counting on solar radiation, I still have to move the air, regardless of the fact, sometimes I use the air to deliver heat or cool, but other times I just need to keep the air moving. So that's kind of a problem, really, with a lot of very tight construction, especially today as we try to do houses that are next to zero energy consumption. We still need to move the air, and maybe move it in such a way that we aren't bringing in a lot of cold from the outside. We have to do all sorts of heat exchanging to try and kind of keep the air at a relatively constant temperature. But the ventilation stuff is absolutely required. Okay, so, and this is actually, if you start thinking about trying to build out into a basement space or an attic space or something like that, a lot of times you end up having to either add ventilation mechanically or through windows. Windows do count. You get to sort of count that a certain amount of it can come through an operable window or something like that. But it all really comes, it's driven by this notion of how much air you can move through. So within that, or framework, let's think about, the design of a system. I'm going to open up that MEP model. I close this up for that overall building. Give you a sense what's happening over there. As you think about a space, we tend to have a couple of different types of systems working together. We'll have return air systems and supply air systems. So supply air systems bring fresh air to the space. Return air systems basically pull the stale air back, okay, so that we can go ahead and recirculate it and kind of keep the air moving. And what will often happen is these systems will tie together in something like an air handler unit, which will be back over at the back end of the system, which has fans which take all the air that have come to it, do some sort of processing of the air, whether it's introducing fresh air or adding some heating or cooling at that point, and recirculate the air back through. So in a typical building, we'll often have these different registers, some of which are supplying air, some of which are returning air, but ultimately are going back through a return air system. So how that works is there are different registers or terminals, and some of those terminals are supplying air, and each of those are related to be a certain amount, 500 cubic feet per minute, whatever it is. Each of the different terminals can supply different amounts of flow based on their sizing, and the number of terminals we need in a room is really determined by just how much air we need to move through. So if I need to move through 2,000 square cubic feet per minute, if I have 500 cubic feet a minute terminals, I need to have 4 supplies, and I need to have 4 returns. Okay. You have to keep the system in balance, because if it gets out of balance, you have that situation where if too much air is blowing into the room and you're not returning it, like either the doors blow open, okay, or you have the situation where if the door pulls in, you actually have to pull really hard because it's sort of blown up against the jamb. Okay. Same thing happens if there's too much return but not enough supply, and you have negative pressure. It would suck the door open all the time or something like that. You need to keep those two systems in balance. And there always is slippage in the system, under the door frames, through the cracks in the windows. They don't have to be 100% perfectly in balance. They're rarely 100% perfectly in balance, but you try to keep them in balance. Because if I have too much return without enough supply, so I'm sucking and I have negative pressure in here, I'm going to start infiltrating. I'm going to pull in air from the outside through all the surfaces and the cracks, and ultimately sort of compromise the building because I'll have a lot of infiltration. So the more you can kind of keep the space inside kind of nicely balanced, so you're not blowing heat out and you're not sucking the outside area, and you try to keep it in balance, the better off you are. So as we try to lay out a system like this, let me just give you a real quick sense of what's going on. So you can sort of see how it works. This is sort of set up in a similar way. There are some of these which are set up as supply, some of these which are set up as return. Let me turn on the filters just so you sort of get a sense of that. I'm going to say that there's the return side, and I'm going to go through and say there's the supply side. And I'll do that same sort of thing on the supply side. I'm going to make those, kind of that pinky color. And then on the return side, I'm going to set up something, just again, so you can sort of see them a little bit better. You get a sense of the different systems here. So here I have 2 basic lines running through, something supplying the red air, the warm air, or the fresh, or the supply side, returning through the blue side, and what's happening in all the different rooms, I'm supplying, then I'm sort of returning to. Very often, just so you know, the way of designing things, we often supply the air out near the surfaces. Okay, so the outside walls where the big windows are and stuff like that, if we're going to heat a space, we tend to sort of put it out to where you're most affected by the external environment, because near those windows, that's where it's going to get cold. It's also going to be where it gets hot. So the conditioned air I often introduce near the outer surfaces that are more affected by the environment. We often pull from the inside, so through the hallway. So you sort of have the fresh air coming to the outside, then kind of pulling back into the center, something like that. And it kind of creates a nice flow of the air. But the way it basically works, just so you get a sense of how these systems get sized, is, let me take out a couple of these pieces for you now. I'll leave it. I'm just going to knock out a piece of the system. Okay, when you go through and you're putting together a mechanical system, it's very much like a plumbing system. You start by putting in some terminals. I'll go to the systems, and I'm going to put in an air terminal. And every air terminal has this whole notion, is it a supply or is it a return? So if, for example, it's a supply diffuser, I'll put it in there. I'm just going to put it on the face of the ceiling for right now. And then what we end up doing is choosing that and connecting it into the system that we want to tie it into. Okay. That one looks like it's actually pretty low flying right now. Because when I put it in there, I don't think I did a good job of saying what the offset would be. Let me undo that. I'll put that in there again paying attention this time to the offset. Oh, let's say 9 feet off of that level. And now I can take that terminal. Notice it has a 12 by 12 in on it. I can say connect it into, okay. In this case it's saying it can't find an auto route solution. Let's talk about why that is, because it's that same sort of issue of the difficulty of making the physics work. In this case, you'll see what some of the problem is. If I'm trying to run the system with a series of hard ducts, okay, the problem is it may have trouble connecting all the elbows and pieces together to actually make a firmly ducted connection between those different things. So kind of like what I was talking about with doing in the plumbing systems, you may have to go through and, do a little kind of hybridization to connect things in there. Where what I can do is take a duct system, get it very close to where it needs to be, kind of rotate that around again, kind of give it some help. It's a little bit strange in terms of the heights right there. But then towards the end, I can go through and run something called flexi-duct between these different endpoints. Flexi-duct is actually sort of a very useful thing. Flexi-duct it's that stuff that kind of almost looks like a dryer vent pipe, where it's like this flexible, hose-like, aluminum-covered, like a flexible duct type system. It's really good because, if there's any imprecision, it allows you to kind of make tighter corners. It allows you to sort of handle the fact that you may not be able to kind of control right down to the last inch where this is, where these hard ducting systems, they really need to be controlled to really get everything to match up. That sheet metal's fabricated down to the nearest inch. So, not as efficient, so we tend not to use flexi-duct a whole lot, but as necessary, we put it in specific locations to get it to make the connection. So we will continue with this notion of HVAC systems and how we design these things next time. But that's the general principle, is really if you can kind of start thinking about the air changes, like we ultimately sort of just determine how many terminals it is that we need to go through and supply that.